So we have in the last lecture we have discussed about conduction heat transfer in a plane wall, and in case of the plane wall the equation for the heat transfer rate was given by this particular equation, and I told you that the heat transfer rate is actually equal to T1 minus T2 divided by L by Ka, where this T1 minus T2 is actually delta T thermal, or we can also call it as thermal potential difference. It is actually thermal potential difference divided by, this is the value of thermal resistance, and this thermal resistance is resistance to the conduction heat transfer in case of a plane wall. So once again I will remind you, we have considered this particular case. This is the wall with the temperature on the left face is T1, on the right face it is T2, and the thermal conductivity of the wall material is K, and the thickness of the wall is actually given by L, and the heat transfer is taking place in a direction normal to the face of the wall. So this is the heat transfer, and then the value of thermal resistance is given by L over Ka. We discussed about this much, and this is L upon Ka. Once again, this is R thermal or conduction resistance, and the uh, reciprocal of it is Ka by L, which is known as conductance. K is the conductivity, and 1 by K is actually known as resistivity. Now we know that the value of K means the unit of K, as a unit of K is given by watt per meter Kelvin. So the resistivity will have a unit which is equal to meter Kelvin per watt. So you need to remember the units also. Now, as I told you that we discussed about the heat transfer due to conduction in a plane wall. Now it is the same topic, but there is a minor change in here. You can read the topic here. It is conduction heat transfer in a plane wall with variable thermal conductivity. In the previous case, we have considered that the thermal conductivity is constant. It is not varying with respect to temperature. Normally, what happens as the temperature changes, the thermal conductivity also changes. So it's written here that K is equal to constant in the previous case, but generally K is a function of temperature. So we can say that K is equal to K naught 1 plus alpha T, where K naught is actually thermal conductivity at some reference temperature, and alpha is the change in thermal conductivity per unit change in the temperature. So finally we can say the thermal conductivity K is given by this particular expression. K is equal to K naught into 1 plus alpha T. So this is the value of the final value of the thermal conductivity, and you can see it's a linear variation in the value of the K. Now once again we come back to the Fourier's conduction equation. This is the Fourier's conduction equation for the case of the plane wall. Once again reminding you that this is the case of plane wall. So this is the wall, the temperature here is T1, the temperature here is T2, the length is L, rather than it's the thickness of the wall. The thermal conductivity of the wall material is K, and heat transfer is taking place in this particular direction, or the direction which is normal to the area of the wall. So if I will make it like this, then it would be easy for you to understand. So I am saying that this is the area I am talking about. I am talking about this particular area. So the heat flow is perpendicular to this area, and this area is denoted by A, capital A. Now we can put the values of the various parameters in this particular equation. So I know that the value of k is equal to k naught 1 plus alpha t. So I can put this value of k here actually. So I can say q by a. I told you q by a, it is q dot everywhere actually. Q dot. What is this value? It is heat flux. It is heat flux rate actually. It is heat flux rate. So and the unit is watt per meter square. So here I put the value of the k. It is k naught 1 plus alpha t dt by dx. Then it's very simple. I can take dx on the left hand side as written here. A can be taken to the right hand side. So minus k 1 plus alpha t into a into dt. Though I am reading the equations here, but my request to you is that you should always try to write all these equations, and only then you would be able to understand these the course in heat transfer very easily. Otherwise it will be difficult for you to understand. Then what we can do is we can integrate this equation. Okay, we can yes, here I can say x is equal to x1 and here x is equal to x2. So basically once again, as I told you, here we can consider the coordinate system, and this distance of the left face is at a distance x1 and this part is at a distance x2, and the difference of x2 minus x1 is actually equal to L. So that is what is written here. So it is x1 to x2, and then what we can do is here the negative sign can be taken out of the integration, and then the value is k naught 1 plus alpha t a into dt. Then once again, when we integrate this particular value, it becomes q x2 minus x1, which is equal to minus k naught a. These are the constants, and then integration of this quantity 1 plus alpha t dt between the limits t1 to t2, because the left face is at temperature t1 and the right face is at temperature t2. So let us see. Once again, same thing is written here. So this was the equation which I just told you on the last slide. So k naught into a with a negative sign here, then we can integrate this. So instead of 1 we will get t, here we will get alpha t square by 2, and the limits are from t1 to t2. And then we can write it is equal to t2 minus t1, the first term, and the second term alpha by 2, it's a constant, can be taken out into t2 square minus t1 square. Okay, and then this t2 square minus t1 square is actually t2 minus t1 into t2 plus t1. So what we have done here is, rather than writing it in this fashion, t1 minus t2, I can write it as minus t1 minus t2. So I have taken t1 minus t2 out of the bracket, this term as well as this term out of the bracket, and this minus sign is converted to plus. So I get k naught a into t1 minus t2, and here in place of it we are left with only 1 here, and here alpha by 2 is remains, and then t1 plus t2 remains. And in the next line once again k naught a into t1 minus t2, and then what we have done, this is t1 plus t2 divided by 2. This is the average temperature, so we are writing it as tm. So this is the mean temperature, and the mean temperature is given by t1 plus t2 divided by 2. Finally we get the expression k naught into a into t1 minus t2 into 1 plus alpha tm. So if you see this particular equation, k naught into 1 plus alpha tm, we can uh, yeah, this is the mean temperature we have set. Then I told you that this value k naught into 1 plus alpha tm, this can be written as km. What is km? It is the mean value of the thermal conductivity. This is mean value of k between t1 and t2. So this is the mean value. So finally the expression, here we were having Q into L. So Q into L is equal to Km into A into T1 minus T2. So finally the expression for the Q comes out to be Km into A into T1 minus T2 divided by L. So if you know the value of the mean thermal conductivity, then you can directly replace the value of K in the first case, which was actually Q dot is given by, here also you can write Q dot, okay, because it is heat transfer rate. So Q dot is equal to Ka T1 minus T2. This was the case when the thermal conductivity was constant. So only difference in this particular case is when we have a variable thermal conductivity value. Then we have to replace this value of K by Km, where Km is given by K naught into 1 plus alpha Tm. So that is the only change which you have to do in case of uh, when the thermal conductivity is variable. Now let us talk a little bit about convection. So when we talk about convection, see, convection occurs mainly between a solid surface and fluid. Now this fluid, as you know, could be either liquid or a gas. Okay, so you need a solid surface and a fluid. Only then the convection will happen. So let us read the definition for the convection. If heat transfer takes place due to transfer of molecules from one place to another, then it is called convection. This mode of heat transfer is more prominent in gases and liquids. So actually, as conduction I said you is prominent in case of solids, convection is more prominent in gases and liquids. That you should always remember. And it is just because of the transference of the molecules from one place to another place. Now, there is a law which governs the convection, and that is known as Newton's law of cooling. So, let us see what is Newton's law of cooling. So, first of all, let us see how we can show the convection to take place. So, here we have shown a solid surface. We have a solid surface here, and we have the surrounding air, which is at a temperature T infinity, and it is also known as free stream temperature. So, T infinity is the temperature of the air, and TW is the wall temperature. Wall means the temperature of the solid surface. You can also say that it is TS, means temperature of the solid surface. And here you can say this layer which is shown by the dotted line. This is a stagnant layer of the air, and the velocity is zero here. This is what is known as no slip condition. No slip condition. The meaning of no slip condition is the velocity of the layer which sticks to the solid surface is actually zero. So no slip condition means velocity of the layer which sticks to the solid surface is zero. Now what is Newton's law? It states that the heat transfer rate per unit area is proportional to the temperature difference. Is proportional to the temperature difference. So what is shown here, we are considering a solid surface where TW is the wall temperature. So I can consider that TW is greater than TS, means the TW is greater than T infinity, where T infinity is the temperature of the surrounding air and TW is the temperature of the wall. So what will happen? The heat transfer from the solid surface will take to the air. Now, this heat transfer is taking place because there is temperature difference. So, the law says that this value of heat flux Q dot divided by A is proportional to the temperature difference actually. So, I can say that Q dot per unit area is equal to H. When I remove this proportionality sign here, I introduce a constant here which is known by H into TW minus T infinity. Now, what is this H actually known as? This H is known as constant of proportionality and is known as convective heat transfer coefficient or film coefficient. Why film coefficient? It's because there is a film of the air. This is the film of the air which has been formed here on the solid surface actually. So You can call it as a convective heat transfer coefficient. You can also call it only as the heat transfer coefficient, or you can also call it as a film coefficient. You can give any name to it. So H is either convective heat transfer coefficient, you can call it heat transfer coefficient, or you can call it film coefficient. So there are three names which I have told you for this H. Now, what are the factors on which actually H depends? Now, this is heat transfer coefficient. It's a function of geometry of the body, physical properties of the fluids like dynamic viscosity, specific heat, thermal conductivity, density, temperature difference. And we can also say that the surface roughness is one more parameter. Surface roughness. So surface roughness also actually is responsible for changing the value of the H. So now you can see what is the value of the Q dot actually. Q dot is now given by, or before that we have said that K is a property of the material. What is K? K is the thermal conductivity, which is more which is the constant in case of conduction process, whereas H is not a property of the fluid. H is dependent upon number of physical parameters, as I have just explained you. So here, as we have written the expression for Q by A as H into TW minus T infinity. So from this particular equation, I can write that Q dot is equal to HA TW minus T infinity. Or I can also say that it is equal to TW minus T infinity divided by 1 over HA. And once again, this TW minus T infinity, this is actually known as thermal potential difference. Thermal potential difference divided by R convective. So R convective, that means this is the resistance to convection. And what is the value of this resistance to convection? It is given by 1 over HA, and it is R convective or convective resistance. So once again, I can write this expression as Q dot is equal to TW minus T infinity divided by 1 over HA. Now, if you will try to calculate the units of SI units of H, H is heat transfer coefficient, and for it the SI unit will be equal to watt per meter square Kelvin, or it can also be written as sometimes watt per meter square degree Celsius. So both these units can be used for heat transfer coefficient. Now, till now we have discussed about the conduction part and the convection part. Now I am going to introduce one new concept which is actually known as overall heat transfer coefficient. Now whenever you consider a plane wall, for example here I have shown a plane wall. I will sketch it once again. So this is a plane wall. Now it is not that the heat transfer will not take place from the surrounding air. Suppose the air or say some other fluid is here on one side of the wall, and on the other side there is air. So this fluid, if I say, is at a temperature, I can say that it is Ti. So it can be the furnace also. So if it is a hot air inside the furnace, so its temperature is Ti, and the heat transfer coefficient on this side is Hi, whereas the temperature of the wall is actually given by T1, and the temperature on the other side of the wall is T2. There are stagnant layers of the hot air on this side, and there is stagnant layer of air on the right hand side also, as you can see it here. And this temperature is actually T naught, whereas this temperature, the wall temperature here, is T2. Okay, so let us try to understand. Here T1 is the temperature of this stagnant layer, T1 is the temperature of the solid surface here, and L is the length of the wall, and K is the thermal conductivity. So what we can do is, see, I think I have not told you about the electrical circuit analogy, or if I have given you, it's okay. See, if I am only considering a wall, so I can say that this is the value of L by Ka. Okay, if I am only considering the conduction part, and the temperature here is T1 and the temperature here is T2. I think I have explained you about it. So the value of Q is equal to thermal potential difference, which is given by T1 minus T2 here, divided by resistance, which is given by L by Ka. And in similar fashion, if I am considering only the convection part in that particular case, you can see it here. If I am only considering the convection part, then I am considering this as the temperature of the wall. Here I have the temperature of the air, which is given by T infinity, and here we have the resistance 1 over HA. So Q convection is given by TW minus T infinity divided by 1 over HA. So basically, this is the value of the resistance, and this is the value of resistance in case of conduction. So let us try to understand how many resistances are there when we are considering the conduction as well as the convection. Now if I see the furnace, the heat transfer from the furnace to the wall will take place because of convection. Then the heat transfer within the wall will take place because of conduction. And then from the outer wall, the heat transfer to the surrounding will take place once again because of convection. So basically, we have the heat transfer is taking place from the uh, air to air actually. So heat transfer is starting from here and it's passing the wall. So it is Q dot. So the same heat will be transferred from the air to the wall, and from the between the wall also it will be because of conduction, and then once again from the wall surface to the surrounding air it is because of convection. So it is a combination of convection, conduction and convection. So we would like to know what is the overall effect of this combined mode of the heat transfer, where convection is also taking place and conduction is also taking place. So now basically we have uh, on the two sides we have convection and in between we have the conduction. So we have basically three resistances, and you can see it here. So I have drawn these three resistances. These are in series actually. These are in series. So the first resistance is the convection resistance or convection 1. Then we have the conduction resistance. Then once again we have the convection resistance written here by RCV2, and it is RCV1 or RCUNV1. And the temperature, initial temperature, we are starting with Ti. Then this is the wall temperature. From here the conduction will start up to temperature T2, and then we have the convection taking place from T2 to T naught. So T naught is actually the temperature of the air outside the wall. So sometimes we call it as T naught, sometimes we call it as T infinity. It depends, because inside temperature, inside the furnace temperature, we have taken to be Ti. So outside the furnace, we are taking it to be T naught. H naught is the heat transfer coefficient on the outside, whereas Hi is the heat transfer coefficient inside the furnace. So let us try to uh, write the various equations for this particular case, the resistances for this particular case. So first of all, we have tried to compare this thermal circuit with the electrical circuit. So this is the electrical circuit. In case of electrical circuit, it is the current which is flowing in the series circuit. The potential difference here is, or the voltage here is V1, here it is V2, here it is V3, and here it is V4. And in between we have the electrical resistances R1, R2, and R3. And the flow of the current is given by the overall potential difference, which is given by V1 minus V4 divided by sum of these three resistances R1 plus R2 plus R3. Same way we can write the value of the heat transfer Q, which is given by Ti minus T naught divided by RC1 plus RC conduction RCV2, which is once again the convection resistance. So it is T1 minus T naught divided by, this is the value of the convection resistance on the inside surface of the furnace. This is the conduction resistance L by Ka, and this is the convection resistance. So finally, this is the equation for the heat transfer rate when there is combined mode of combined modes of are there for heat transfer to occur, that is conduction and convection. Now we want to calculate what is the overall effect of it. So what we do, we write this equation. Now we take the previous equation, you can see it, A is here. Okay, so A is common because it's the plane wall case, so A will remain same. So this A can be brought here So in the next slide here, you can see Q by A is given by T1 minus Ti divided by 1 over Hi plus L by K plus 1 by H naught. And here we can write it is equal to delta T over divided by R over all. Okay. So once again, same diagrams which I explained you earlier also. So now let us, this is one way of doing this calculation actually. We have calculated the value of Q dot. We can also have done it in a different manner. So first of all, we are writing the value of T1 minus Ti minus T1. So this is the first resistance. This is the wall here. Just try to understand here. The temperature here is T1 and here the temperature is Ti. And here we have the convection part. Here we have the convection. So Q convection will be given by Ti minus T1 divided by 1 over Hi into A. Now you just try to see what is the value of Ti over T minus Ti. So this is the value Ti minus T1 is equal to Q into Hi over Ai. Similarly, I can write the value of T1 minus T2. How? I know then in the wall the conduction is taking place here for this much portion, and this is conduction, and in conduction Q conduction is will be given by T1 minus T2 divided by L over Ka. So if you will calculate the value of T1 minus T2, it will come out to be Q conduction into L divided by Ka. So you can see it here. So this is the value of Q divided by Ka over L, or this is also equal to Q into L divided by Ka, one and the same thing. So the dots are not here. You have to put it. You have to use it. Similarly, then from the wall of the furnace, the heat transfer is taking place to the surrounding, which where the temperature is T naught, and it is once again because of convection. So now I can write Q dot divided by H naught over A naught, similar to this particular equation which I have written here. Now what I can do is I can add all these three equations. So T1 and T1 cancels, T2 and T2 cancels, and we are left with Ti minus T naught. Q can be taken as constant, common from all these three values. Q has been taken constant, and here we have 1 over HI. You can actually in AI is equal to A naught is equal to A. So that is the condition here. So rather than writing AI, you can write A also, multi plus L over K 1 over H naught into A. So once again you have obtained the same equation which we have written here in this manner. So whether you use the um, equation which we have derived from the Fourier's law or Newton's law of cooling, or we can also use the equation of um, that we use in case of electrical circuits. Okay, so both ways are equally good. Now what I want to say here is I want to calculate the overall heat transfer coefficient. Now what is overall heat transfer coefficient? In which we are considering the effect of H also and K also. So H and K, when the combined effect is taken for both these, then we call this as U. So overall heat transfer coefficient is represented by U actually. So I can say for from analogy of the heat transfer, I can say that like in case of convection, the value of Q dot is given by HA into TW minus T infinity, which is actually equal to HA into delta T. So I can replace this H by U. So I can say that Q dot is given by U, which is taking into account the conduction as well as the convection multiplied by the area into Ti minus T naught, because this is the overall temperature difference in our present case. So I can say Q dot is equal to Ti minus T naught. This is the equation which we derived earlier. Now when we compare both these equations, so you can see the value of U is equal to 1 divided by uh, 1 over Hi plus L by K plus 1 over H naught. So this is the value of U. and this value of the u is taking into account both heat transfer coefficient for the inside as well as for the outside, and this is very very important. Now we can also consider only a composite wall. In case of composite wall, we are considering that this is the heat transfer coefficient on the outside and this is the outside temperature, whereas on the wall surface this is the temperature Ti. In interface the temperature of the another wall it is T2, here the temperature is T3, here the temperature is T4, and their thicknesses is L1, L2, L3, and the thermal conductivity of three walls are K1, K2, and K3. And outside it is the heat transfer coefficient which is at H naught, and the temperature here is T naught. And this is very similar to the case of our household wall, where you can say this is the brick. Okay, this is cement which you have applied, and here also you have this cement. Rather there can be two more layers, one could be of the whitewash on this side and other could be the whitewash on this side, which we have not considered in the present case. So I can write the value of q dot which is given by overall heat temperatures difference, which is Ti minus T naught. And how many resistances are there? There are five resistance. First, this is the convection resistance. This is R convection one. Then we have conduction resistance. Then once again we have, this is R1 conduction. This is R conduction 2. Then we have R conduction 3, and then we have the convection resistance R convection outside. This is inside. Okay, so the values are known to us. This is 1 over HIA. The value here is L1 by K1A. The value here is L2 by K2A. This value is L3 by K3A, and this value is equal to 1 over H naught into A. So, and what is the value of the heat transfer? This is the thermal potential difference, and this is sigma R thermal. So this is the first value of the resistance, this is the second resistance, third resistance, fourth resistance, and the fifth resistance. So this is the value of the sigma R thermal, and then we can calculate the value of U. And U, once again, we can have two values of the U. One is Ui, and one is U naught. And Ui is overall heat transfer coefficient based on inside area, and U naught is equal to overall heat transfer coefficient based on outside area. And if we want to write the value of u in this particular case, we can also write that. We know that we can write q dot is equal to u a ti minus t naught. And the previous equation, the value of you can see the value of q dot is given by ti minus t naught divided by 1 over hia plus L1 over K1A plus L2 upon K2A plus L3 upon K3A plus 1 over H naught into A. And you can see this A is actually will cancel out here. This A will cancel out, and the value of U will be given by 1 over 1 over H I plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 over H naught. So this is the value of the overall heat transfer coefficient in case of multi-layered wall. And let me tell you, whether you calculate this value on the basis of inside area or outside area, it is same actually, because sometimes we use the terminology that which is valid in case of cylinder. Actually, when we use ui or u naught, this is very much valid in case of heat transfer in case of cylinders, that you will understand in the forthcoming topics actually. Now let us talk something about the radiation heat transfer in case of radiation. Now what is radiation heat transfer? In conduction and convection we need a material medium to transfer energy. Heat may also be transferred through regions where perfect vacuum exists. The mechanism in this case is electromagnetic radiation. That is electromagnetic radiations or waves which is propagated as a result of temperature difference, that is thermal radiation. So because of the thermal radiations, the heat will be transferred. Now what is this? This is actually Stephen Boltzmann's law of thermal radiation, and this is responsible for the radiation heat transfer. What does it says? It says a black body will emit energy at a rate proportional to the fourth power of the absolute temperature of the body and directly proportional to the its surface area. So let us see what is it saying. It says that energy emitted energy emitted by the black body is proportional to area of the black body into T raised to power 4, and it is applicable only for black bodies. Or I can say that Q emitted is equal to sigma into A into T raised to power 4. When we remove this proportionality sign, we put this sigma, which is actually known as Stephen Boltzmann's constant. So this is the value of the Stephen Boltzmann's constant. This you need to remember. Sigma is 5.669 into 10 raised to power minus 8 watt per meter square Kelvin raised to power 4. Above equation gives thermal radiations emitted by a black body. The net radiant exchange between two bodies will be proportional to the difference in the absolute temperature to the fourth power. Now, see, till now we are saying that we are considering only a single black body. I am saying that if I have a black body and its temperature is T1 and its surface area is A, so I will say that energy emitted by the radiation is given by sigma A into T raised to power 4. Now, suppose we have two black bodies. One is here and another is here. Its temperature is T1, its temperature is T2. Its area is A1, its area is A2. But I can say that I want to calculate the energy which is transferred from A1 to A2. Actually, what is happening in this particular case, the energy is also coming from T body 2 to body 1. So it's we would like to calculate what is the net exchange of the heat transfer from the body 1 to body 2. So let us see how we are going to calculate that. So that is net heat exchange is proportional to, once again, area T1 raised to power 4 minus T2 raised to power 4, and we are considering them to be black bodies only. So Q net exchange is given by sigma A into T1 raised to power 4 minus T2 raised to power 4. This is how we calculate the net heat exchange. Now, this is the case when we are considering it as a black body, and you must have studied in the previous classes that in case of black body, the emissivity is actually equal to 1. Emissivity stands for the emission power. Okay, and you must know that in case of a black body, the energy absorbed uh, is equal to energy. What do you call energy emitted? So basically, in case of a black body, uh, absorptivity which is given by alpha is always equal to epsilon, which is actually known as emissivity, and its value is always equal to 1. So absorption is also maximum in case of a black body. Now all other bodies may not be black bodies, they may be gray bodies also. So in case of a gray body, how we are going to modify this particular equation which is given here, q net, which is equal to sigma a T1 raised to power 4 minus T2 raised to power 4. This is the equation which is valid only for the case of black bodies. Then what we do in case of gray body? Gray body is a body for which the emission value, epsilon value, is not equal to 1 actually. Okay, and here we introduce a factor f epsilon. You can also write it as epsilon only or f epsilon. It is one and the same thing. same thing, and it is known as emissivity function. And this emissivity function, this value is always less than 1, because for gray body epsilon cannot be equal to 1. And there is another factor which is represented here as Fg, which is, it is actually known as view factor. Now what is the significance of this view factor? This we will study later on also, but here I would like to tell you, this is also known as shape factor or orientation factor. Orientation factor. So basically, see, we can have two gray bodies with us. uh, just a minute, I will include, I will introduce a slide here to explain you this. Okay. Now what we can do is, so suppose for example I have a body here, and this is another gray body. This is gray body 1, this is gray body 2. Okay. And though I have shown them to be parallel, but normally what happens, the bodies can be oriented in a different way. Suppose one body is uh, looking like this, means it is radiating energy here from in this direction. Other bodies here, okay, it is radiating energy here. So you can see they are oriented in a different way. Actually this is inclined, this could be vertical actually. So there may be some amount of the energy which will be reaching here, but not all the energy will be reaching here. So we because of the orientation, the energy which is being emitted by the body one may not be totally reaching to the body two. And because of their orientation, we have to introduce one more factor, and this factor is actually known as the shape factor. And because of different shapes, means because of the different orientations or the way the bodies are put, the energy which is leaving the body one may not be in totality reaching to the body two, and this is taken care with the help of the shape factor. So finally we can say that q net, which is exchanged between two gray bodies, is given by sigma into a into f g into f epsilon into t1 raised to power 4 minus t2 raised to power 4. So basically we are saying that temperature T1 is greater than T2. So some part of the energy from the 2 is also reaching to 1, but the energy which is leaving 1 is more than um, energy which is coming from 2. So net heat exchange between two gray bodies is given by this particular equation. We will discuss this in more detail when we will study uh, radiation part. Now I am going to discuss about the conduction in a plain hollow cylinder. Now plain hollow cylinder, it's a very simple case. So what we have shown here is we have a cylinder here, hollow cylinder rather. So this is the you can say central axis of the cylinder, and this is the solid part of the cylinder. Okay, this is the solid part, and here the fluid can flow through it. Fluid can flow through it, and inside radius of the cylinder is r1, outside radius is r2, and the length of the cylinder is actually l. And if we see the side view, it would look something like this. This is something like this. So I can say this is the uh, solid part, and here we have the hollow, and we can say that the temperature here is T1, whereas the temperature here is T2. And we also say that the heat transfer is taking place only in the radial direction. This is the direction of the heat transfer q dot, and we also say that T1 is greater than T2, and the thermal conductivity of the cylinder material is K. So now we want to calculate the value of the heat transfer. So this is the Fourier's conduction equation for a plain hollow cylinder minus Ka dt by dr. So we have replaced dt by dx by dt by dr, because now the heat transfer is taking place in the radial direction. Now we can consider any radius r, any radius r from the center which is at a distance center, any area surface which is at a distance r from the center, and its thickness is dr. So we want to calculate how much heat is being transferred through this surface. Now, what is the area in the radial direction? It will be given by 2 pi r. This is the circumference multiplied by the length. So, because the heat transfer is taking place in the radial direction, so this is the area through which the heat transfer is taking place at the radius r, multiplied with minus k dt by dr. Now, it's quite simple once you have understood this fact. Uh, so then I can take this r and dr on the left hand side. So I get q into dr by r. So once again I am changing into q dot, and on the right hand side we are left with minus k 2 pi l into dt. So for calculating the heat transfer, on the left side we can say that the heat transfer is taking place from radius r1 to r2 dr by r, and on the right hand side k into 2 pi l, we are considering that the thermal conductivity of the material is constant. It is not varying with respect to temperature, and here we can say dt for, and it is integrated between t1 and t2. So you know the integration part, it will be give us q dot log natural r2 by r1 minus k2 pi l into t2 minus t1. So finally the answer for the q dot comes out to be 2 pi k l t1 minus t2 divided by log r2 minus r2 by r1. So this is the equation, and this we can write in a different fashion also. I can say that this is the temperature at the inside radius r1, this is the temperature at the outside radius, and in between the conduction is taking place. So what is the value of q actually? Q can be written as t1 minus t2 divided by log natural r2 by r1 divided by 2 pi k l. So this is the thermal potential difference divided by r thermal. So this is the value of the resistance in this particular case. So T1 minus T2 is the thermal potential difference, and this is the value of the uh, R thermal, which is given by log R2 by R1 divided by 2 pi KL. Then we can consider the case of a cylinder actually, where both convection as well as the conduction is taking place. So we have considered it as a double layered cylinder. So I will try to explain you this diagram. So here we have the inner cylinder, and here we have the outer cylinder. Okay, this is solid surface here. Here also we have the another cylinder surface, and you can say that the inside radius is r1 here, this is r2, and this is r3. And we can say the temperature here is T1, temperature on this surface is T2, temperature on this surface is T3. And let us say to the perpendicular to the um, and inside there is a fluid which is and its temperature is Ti, and heat transfer coefficient is Hi. So and outside the cylinder the we have the air, and its temperature is, let us say, T naught, and its heat transfer coefficient is H naught. So basically, first of all, from the fluid to the solid surface of the cylinder, inside cylinder, fluid to um, cylinder, heat is being transferred because of convection, and within the cylinder it is because of conduction, and then the second cylinder it is also because of the conduction, then outside it is flowing just because of convection. From the this surface of the cylinder to the surrounding air, it is because of the convection. So inside, the first resistance will be because of the convection, second is conduction, third is conduction, and fourth is convection resistance. So we have four resistances, and then we can say that K1 is the thermal conductivity of the inside cylinder, and K2 is the thermal conductivity of the outside cylinder. So we have four resistances. So first of all, we can show these four resistances here. This is the case of the compound cylinder with convection as well as conduction. So we have written all the temperatures T1, Ti, T1, T2, T3, T naught, and this is the first resistance 1 over Hi A1. The second resistance is because of the cylindrical surface, which is given by log natural R2 by R1 divided by 2 pi K1 L. Now L in this case, this is the length, this L will be constant. So you need not to write L1 and L2. Actually, it is L. It is L only. Here also it is L only. So this is the second resistance, log natural R3 by R2 divided by 2 pi K2L. And the fourth and the final resistance is 1 over H naught into A naught. So remember it, the area is not same, and here you can write AI actually rather than A1. You can write AI because this is the inside area and this one is the outside area. So finally we can calculate Q dot, which is given by Ti minus T infinity T naught, because this is the thermal potential difference. So that is the overall thermal potential difference divided by, this is the value of sigma R thermal by analogy to the electrical circuit. Okay. So 1 over HIAI log natural R2 by R1 2 pi K1L log natural R3 by R2 2 pi K2L and 1 over H naught A naught. And this can also be calculated using this particular equation. This is actually your, do you remember that Q in case of cylindrical surface, in case of convection is given by 1 over HI AI, and here you can say delta T. This is convection part, and if I write the conduction equation, this is given by delta T divided by log natural R2 by R1 divided by 2 pi KL. So you can simply see, if I first, it is the convection part, this is the convection equation, and here also inside the first resistance is because of the convection. So I can write Ti minus T1 is equal to Q dot into 1 over HIAI, and this you can get from this particular equation. You can see it here. You can easily understand why I have written it like this. Similarly, T1 minus T2 is given by Q dot log natural R2 by R1 divided by 2 pi K1L from this particular equation. And once again, this is also because of this particular equation only. This is the general equation, you can say. So T2 minus T3. Similarly, T3 minus T naught, now this is T naught actually, is given by, and this is convection because here the from T3 to T naught it is convection which is taking place. So T3 minus T naught is equal to Q dot into 1 over H naught A naught. So finally I can add all these equation and I will get Ti minus T naught is equal to Q dot into all these resistances. Okay. And then finally I can now put the values here. This is the value of the Q dot Ti minus T naught. Okay. And these are the various resistances which comes in the denominator. Now I can also say that this Q dot is also given by UIAI into delta T, or U naught A naught into delta T, where what is this U? U I have already explained you. It is known as overall heat transfer coefficient. Overall heat transfer coefficient. And this overall heat transfer coefficient is U. Now because the inside area and the outside area are different, so we are defining two different overall heat transfer coefficient. One is based on the inside area, which is UIAI, and other is based on the outside area. And let me tell you, UI will always be greater than U naught because AI is less than A naught. So that will always happen. So you can use any depending upon your choice. So if we compare the first equation and the second equation, we can always calculate the value of UIAI, which is given by this particular equation, and UI will come out to be this value. Here what we have done, we have also put the value of AI. So if you see, AI and AI will cancel it. This is 1 over HI over AI. And here we have put the value of A naught, which is equal to 2 pi R3 into L. So you can see it here. If I put the value of AI, because AI will be coming here, it will be equal to 2 pi R1 into L. So this is how we can easily calculate the value of overall heat transfer coefficient based on inside area or outside area. Now this is the case of the hollow sphere. I will do it up to here only. Hollow sphere. Now hollow sphere is also a very simple application. Hollow sphere means it is similar to that the case of a cylinder, but sphere is different thing like ball. So it's a case of a ball. You can say inside temperature here is T1, here the inside temperature is T2, and the thickness of the wall is of particular material for which the thermal conductivity is Ka, and you can say that the inside radius of the sphere is R1, outside radius of the sphere is R2. Now I want to calculate the heat transfer. Once again, I am considering that the heat transfer is taking place in the radial direction. It is in the radial direction. So let us calculate what is the value of heat transfer in the radial direction. So once again, I can write this particular equation: Q dot is equal to minus Ka dt by dr. Only difference here is that this area is different now. In case of cylinder, it was 2 pi r l, but in this particular case, it is 4 pi r square. So we can put uh, area equal to 4 pi r square. Other things remaining same. You can take dr and r square on the left hand side here. Then we are left with minus k 4 pi dt, and then this is the simple integration. You can just see it. So finally, when you do all these steps, you can see finally this will be the answer actually. Q dot will be given by 4 pi r1 r2 k t1 minus t2 divided by r2 minus r1. So this is the final equation, which we can also write as t1 minus t2 divided by r2 minus r1 divided by 4 pi r1 r2 divided by r1 r2 into k. So this is the value of the heat transfer in case of hollow sphere because of conduction. So now I am going to write for the plane wall, Q dot is given by delta T divided by L by Ka. This is the case of plane wall. Second case is for the cylinder where the value is delta T divided by log natural R2 by R1 divided by 2 pi KL. And now the third case is for the sphere, in which case Q dot is given by delta T divided by R2 minus R1 divided by 4 pi R1 R2 into K. And this is the value of thermal resistance in case of sphere. So I think this much is sufficient for today. So you can go through the lecture, and then we will discuss the remaining things in the next class.